Hello, everyone. Are we ready to start again, Mary-Rose?
Yes, we are. Thank you.
We are here, yes.
You can stay until the workshop to find out how it works. We can show them what Mr. George is showing everyone, our robots. Let's go. Okay. We have seen what a robot has: an actuator, a sensor, an arm, a leg, a wheel, and so on. But how do we control that? We have a controller, which is the brain of the operation. It's a computing unit that controls the motion of the robot in a programmable manner. And it could be microcontrollers, specialized controllers, or it can be a whole computer. Here we have some methods. It's the main types of control systems used in robotics. We have the open loop control systems and the closed loop control system. This is what an open loop control system looks like. The control system has a lack of feedback. Means that the robot movements are determined solely based by the input commands. So it does not send feedback back to the controller. This is simple, very simple. It gets the signal, it sends out the signal. And these are the advantages. Simple, reduced system complexity, as it does not require the feedback part. And of course, since it's simple, it has lower cost. But the disadvantages is that it cannot compensate for the errors that occur during the operation. So it has reduced accuracy and reduced repeatability. These are used in applications where they need a low precision and the risk of errors are minimal. So they use this for pick and place robots or assembly and stuff like that. And we have control systems, which have feedback mechanism and are more complex algorithms that monitor the movements in real time. So as you can see here, it has the input, the controller, it does control the output, and then it says feedback at the same time. So the feedback and the input work simultaneously, and they compare what it does. And here is the advantages. It can compensate for errors, as I said before, and it has high accuracy and repeatability. The disadvantages are that the more complex hardware and software, and therefore it increases the cost. These are used in high precision, accuracy. Sorry, I was wrong. Assembly is uses closed loop inspection, machining. I'm guessing medical robots as well, because they need high accuracy, and so many more. We also have different controller types. We have the proportional controllers, the integral, and the derivative controllers. The proportional controllers are proportional to the error. Integral controllers have time, so they correct over time. And the derivative, they detect and resist abrupt changes in the system. They have also combinations, proportional integral, proportional derivative, and the most complex and the most knownly used now is the proportional integral derivative control, PID. That looks a bit like this. So it has, it reads the sensor, it computes the desired actual output by calculating proportionally, integrally, so over time, and derivatives. So it does have the responses, the changes in the system. All those together, of course, it gives more accuracy in the system, the output. Okay, all those need complex maths. As you can see here, there are deviations, complex maths. And complex maths also bring complexity to the system. What we need is something that has less maths. It's more simple. So there's another concept that's called fuzzy logic. Fuzzy means not clear, distinct, or precise. It is blurred. And in the robotics is an approach to variable processing that allows for multiple possible truths. Multiple sources of truth values to be processed through the same variable. So I'm going to give an example. Everyone knows Boolean logic, right? Is it hot? Yes or no? It's 0 or 1. But fuzzy logic, it says, is it hot? Very much, 0.19. Fairly so, 0.75. Moderately, somewhat, very little. So this is obviously it's better than Boolean logic that it's only true or false. But it's much simpler than using those complex mathematics that you use in controllers. Another important thing that I didn't mention is how does the robot work? So it needs an energy source. It can use electric batteries, power adapters, solar power, wireless, pneumatic, and hydraulic. I mentioned those. And here are some examples. Electric generator, solar cell, and so on. Now we're going to move to the programming of those controllers and the simulations you can do. So we have the programming languages. The most common are C, C++, Python, Java, Scratch, and MATLAB. Programming environments, Arduino IDE, LabVIEW, RoboDK, ROS are the most popular. So what does our RoboDK do? It's an offline programming and simulation software for industrial robots. You can use it for many applications. They have huge library that has most of industrial robots. Like one of them is KUKA. And it has examples. So it has a pre-program and pre-simulations of robots like this one. I will show you one later as well. And you can, when they have a simulation, they have a program, you do it step by step. It's not like a code. You just press your end effector, you move it to a 1 position, and then you set it as a target. So that's how it works. It doesn't require very difficult programming languages and so on. So everyone can try and use it. And of course, you need to remember all those things we said about kinematics, dynamics, how does it move around, the rotational and the translational, because you might need to rotate and so on. It's very easy. I will show you an example later. We have ROS, the robot operating system. This is very much more complex than RoboDK, because this one you actually program as well. It's not just a simulation. It's an open source meta operating system for robots, and it provides all those services like hardware abstraction, low-level device control, implementation, message passing, etc. So the main thing you have to keep from this is ROS is a platform that supports code to be reusable in robotics and in research and in education. So everyone can share their code. It can be manipulated, it can be reused. It's very, if you have knowledge of robots and programming languages, it is very good and is suggested to be used in robotic versions. Here you can see what it includes: motion planning, computer vision, data logging, machine learning, and all those things. And I will try to explain a bit of the concept that are used in ROS. They are the nodes, the messages, the topics, and the services. The nodes communicate with other nodes, and they perform a computation. They send, the messages can communicate, nodes can communicate with passing messages. Topics can subscribe and publish a topic. Services has to do with the service clients, and master is the provide a name and registration. You can see there that the messages are published and subscribed, and they're sent to different nodes. And here you have our RVs, which is a 3D visualization tool in ROS. So of course you can already tell it's much more complex than ROBOTICS. This has actual depth and image processing. It's not just a robotic arm. It is used in education, but is used in research as well. So we mentioned all of those things. They come together: the sensing, the understanding, the acting, the learning, and the technology. I'm going to give an example of the Atlas robot that has sensors. It has LiDAR sensors, stereo cameras, and it has, for the actuation, it has wrists, hands, hydraulic actuators. It also has protective cage, low-set arms, and has wireless antennas and onboard battery. So you can tell that that robot can jump, but it is very complex, and I will show you why. Because it requires 2 computers in order to work. It has one on board and one on the control station, because it has a very fast and very complex behavior and dynamic. That's why it needs so much computational power. I suggest you check this out. Actually, it's very interesting how it works. And here are the sensors that we mentioned.